So, to evaluate this constant b, I am going to take my definition of my Green's differential equation over here and do a integral, okay. And that integral is going to be, what kind of an integral should it be? 1D, 2D, 3D, 2D integral, right. So, this is going to be an integral, okay, over S ds. What kind of a S should it be? Where is my singularity? Origin. So, I should include it, right. So, the easiest symmetrical way of doing it is to have a circle, okay, of radius epsilon, okay, epsilon is some small number, and integrate about this. So, I will call this surface to be S infinity, okay, sorry, not infinity, S epsilon. That is what I am going to do, okay. So, evaluating these integrals requires some little bit of care, okay. So, the first term over here, when it integrates, I am going to call it term A, the second term I am going to call term B, and the third term over here I am going to call term C, okay. So, we will individually go over A, B, C and do a budgeting to get B, that is the approach that we are going to take, okay. So, let us look at the first term for A. So, it's saying what? Now, I will just write one integral symbol, okay, let it be, we will just be consistent, we will write del squared g of r integrated over ds. What is ds in polar coordinates? R dr d theta, right. So, this is r dr d theta, okay. Is there any theta dependence? No, right. So, that integral over d theta we can immediately write as 2 pi, right. So, I am going to write this as 2 pi, okay, and del squared g of r dr, that is what I have to evaluate, okay. And this is over r. So, that could be one way of doing it, okay, but the trouble is I still have this del squared g sitting with me, okay. Another way of doing it could be, if I look at this term over here, can I think of, first of all, can I write this del squared g as the divergence of a vector, right. This follows from the rules of vector calculus that del squared g can be written as the divergence of grad g, okay. You can just write out the operators, take the dot product, you will get exactly this, okay. So, what am I doing now? So, when I am doing integral of del dot grad g ds, what theorem of vector calculus comes to mind? It is a divergence under a closed volume, or in 2D closed surface. So, which theorem? Divergence theorem, right. So, divergence theorem will convert this del dot something into the outward flux, right. So, this will become outward flux of what vector? Del g dot n hat and dl, right. So, one route was what we were trying over here, splitting it as into r and theta. Another route is this route, okay. This route seems to be little bit more intuitive because I have reduced the integral straight away. What is n hat over here? R cap, exactly. So, n hat is, for example, always pointing radially outwards. So, that is my n hat is equal to my r hat, okay. What is the definition of del g in polar coordinates? This one is not that difficult. Del g in polar coordinates, the first term is simply dou g by dou r along r hat and 1 by r dou g by dou theta along theta hat, okay. So, you know n hat is r hat, theta hat has what relation to r hat? Perpendicular, right. R hat and theta hat are perpendicular to each other, right. So, only one term is going to survive from this integral, and that is going to be del g by del r, right. So, this is going to become integral del g by del r, right, and what else do I have over here? That's about it, right, and this will become a dl, right. Now, I am going to choose epsilon to be much less than 1, like epsilon is very small, it is just enough to include the singularity, right. So, I am going to keep epsilon very small. Okay. So, here is another approximation that I will tell you, that I will use. So, h naught 2, right, that is the function that I have, right. There exists a asymptotic form for this when x is very small, okay, and that is based on the fact that j0 of x is approximately 1 when x is much less than 1, and y0 of x is approximately 2 by pi log of x. Okay. Again, this is just information I am giving you, which this is very well documented in various mathematical handbooks, okay, asymptotic forms of special functions. Okay. So, what do I do next? I will use this form, and you can see that the second this y0, you can see that it has the correct singularity kind of a shape, right. As x tends to 0, what happens to log of x? It goes to minus infinity, undefined, right. So, it is capturing the singularity well, and j0 is a finite quantity 1. Okay. So, from these two terms, what survives is going to be, so let's write it down over here. So, del g by del r, that is what I have to do. Okay. So, del by del r of 1 plus 2 by pi log of kr dl, that is what I have to do. I have just substituted the form of g. So, the first term goes away, second term what will I get? Oh, you are right, yeah, there should be a minus j here, right, because because of the way that I have defined h2 is j minus jy, right, that is right. So, the first term goes away when I take the d by dr, second term will give me what? What is the derivative of log kr with respect to r? K, right. So, I am going to get a minus 2 j k by pi, okay, into 1 by kr integrated over dl. Okay. What will this integral over? I am now doing this integral only on the surface, right. On this surface the value of r is constant, right, on the line rather. So, what will this integral evaluate to? Integral dl will just simply give me 2 pi r, and r is equal to epsilon, right. So, we will just write this as minus 2 j k by pi into 1 by k r into 2 pi r evaluated at r is equal to epsilon. What am I left with? K goes away, pi goes away, r goes away. Okay, r is small but finite, so I can cancel r in the numerator and denominator, right. So, what am I left with? Minus 4j. Is that clear? So, remember, the meaning of this is del g by del r evaluated at all points over here along the circle boundary, right. There is no variation. So, this integral over dl simply becomes 2 pi r. Okay. R is not varying. If r were varying, then it would be a different thing. R is constant over here. So, it is more like an integral over d theta over here. So, I get a minus 4j. So, term A evaluates to minus 4j. Then we come to term B. Okay. Now, term B is where we can use our this r dr d theta approximation. Yeah. There will be a b, yeah, right. Yeah, g has a b everywhere, that's right. So, the b will come in over here.
Minus 4jb.
Yeah, exactly, very good. So, there is a b over here and there is a b over here. Yeah, okay, very good. So, let us come to the b term. So, I have a k squared integral over g of r dr d theta. right? And again I can write this as 2 pi k squared integral g of r dr. Okay. Yeah. No, that's here. Integral over dl give me 2 pi r. This is what we started evaluating. So there is no additional 2 pi, right? The 2 over pi has been taken into account over here. Okay. Okay. So again, what do? I have a special form for g. I'll just substitute that, right? So 2 pi k squared integral r and 1 minus j2 by pi log of kr. This time I should not forget the b and a dr. Yeah, that is my g. B times Hankel 2. Hankel 2 is j minus jy, and j is this and y is this over here. No, we didn't follow this approach. We followed this approach where we can use the divergence theorem to convert it. So that is the 2 pi that you were referring to. Yeah, we didn't use that approach over here. We use that approach for the term b. Okay. So this is the approach that we used over here. So let's write it over here. Now when I look at this expression, let's just gather all the constants outside. So 2 pi k squared b I can take out. Okay, and then finally I have an integral of r dr, right? And then I have an integral, so 0 to epsilon, and then I have a term which is j2 by pi integral r times log of kr dr. Those are the two terms, right? Now, without actually doing all the math, you can see what will happen to the first term over here. Integral r dr will give me r squared by 2 evaluated epsilon and 0, and I am going to take the limit epsilon tending to 0 eventually, right. So, we are going to take limit epsilon tends to 0, that is going to happen anyway. Okay. So, this first term over here is tends to 0 as epsilon tends to 0. Fine. Then the other term that I have to worry about is integral of r log kr. Okay. So, what can we do about integral of r log kr? I mean, we can just integrate it. We know how to integrate this, right? We can take log as the first term, integration by parts, right? So, this if I just let's just look at this term over here, okay. Otherwise, I will have to keep writing the constants each time. So, the square bracket term I am writing over here. So, first term, okay, multiplied by integral of the second function, right. So, I am taking this as the first function and this as the second function in integration by parts. So, log kr multiplied by integral of second function, which is r square by 2 evaluated between 0 and epsilon, minus integral 0 to epsilon derivative of the first function, right, which is going to give me a, what is it going to give me? 1 by r, right, the k will cancel, yeah, multiplied by r square by 2 dr, right. Okay. Now, what happens over here is there are, so is equal to this. Let's look at the second term over here. Second term is going to cancel off 1 r. I will be left with a r dr by 2. R dr by 2 integrated 0 to epsilon. What is going to happen? This guy is going to tend to 0. Finally, what am I left with? R squared log kr, right. So, r squared log of kr, that is the term that will have to be evaluated at 0 and epsilon. How do I evaluate this function? Is there some, are you reminded of some way of evaluating this limit as r tends to 0? L'Hopital's rule, right? So first I have to get it into a 0 by 0 form, right? So I can do that as, so limit r tends to 0, this becomes log of kr by 1 by r square, right? So either 0 by 0 or 0, I mean infinity by infinity form, whichever way, right? So derivative of each term, so first term will become 1 by r, second term will, the term in the bottom will become minus 2 by r cube is equal to minus r squared by 2. So what is its limit as r is equal to 0? 0, and at epsilon it will be minus epsilon squared by 2. So what is its contribution? Overall 0, right? So all of this hard work is going to give term B, right? Term B is equal to 0. Okay. So this is, I mean, we have gone through a lot of very this is basically class 12 math, right? L'Hopital's rule and integration by parts and all of that, right? So it's not very complicated, but just notice what happened. G is your Green's function. We've physically seen that it has a singularity at 0 because that Bessel y function was going to 0. Even though the function is singular, what is the integral of that function? It's finite, in this case it's 0, right? It's just like a delta function. The delta function is undefined at the singularity, but its integral is finite. Similar thing has happened over here. Okay. So next we will look at the remaining terms and put them all together.